Regression says that buried within this scatter plot is the actual regression line, like this one, which would be the line obtained for the entire population of men from which we've sampled. And at any particular dosage, 20 milliliters per day, say, the population mean new follicle count equals this, the value of the line at x equal 20. Since we're letting this line represent means of y, new follicle counts, we have to be careful with the interpretation of the A and B model coefficients. While A is generally the value of y when x equals 0, here we must specify that it's the mean of y when x equals 0. Furthermore, our slope, B, is the mean change in y associated with a 1 unit increase in x. Now then, what does regression look like in practice? Because we're just pretending here that we know the actual regression line. In the real world, just like we have to estimate population means and SDs and other parameters, we need to estimate A and B. And how should we do that? Well, a sensible approach would be to estimate A and B from the line that fits our scatter plot best. And the standard way to define a best fit in our setting is called least squares. The least squares regression line is the line that minimizes the squared vertical differences between y and the line. Squared vertical differences, as in the square of the length of all these red line segments. If the line doesn't fit well, like this, say, the squared differences will add up to a big number. Comes out to about 2839 here. What we'd like to do is find the line that corresponds to the smallest possible sum of squares. Turns out it's the one we started with a sum of squares value of about 554.